Hello! What I want to do in this video is go ahead and show you how Gaussian elimination works on matrices in order to solve linear systems of equations. So previously we solved this linear system of equations and found a parameterized solution set for it. And so we want to do the same thing but do it with linear systems. So here we have our linear system of equations, and we want to write down the augmented matrix associated with it. So here it is. Remember, we're just taking the coefficients of each linear equation, and also to the right of this bar, write what's on the right side of the equality, the constant term. Sometimes you won't actually see that bar. I like to write it just to highlight where that equal sign goes. So what are we going to do with this? We're going to try to find a row equivalent matrix to this one that is in row echelon form, and we're going to do so by only using three operations. We may interchange two rows, we may multiply one row by a non-zero constant, or we may add a multiple of one row to another row. So we're going to try to put this matrix in what's called row echelon form. So we want leading ones in each row, and the leading one in each row needs to be to the right of the leading one in the row above it. So we already have a leading one in this first row, meaning that reading from left to right, the first non-zero entry I get to is a 1. And after that, there should be all entries below it should be 0. So we want that 3 to be a 0. And we do that by taking row 3 and replacing row 3 with row 3 minus 3 row 1. Okay, so when we do row 3 minus 3 row 1, row 1 and row 2 remain the same, so I just rewrote those. And then row 3 is replaced with 0, 4, 6, 0, 10. If you go back to video where I did the same linear system of equations, but on a linear systems level instead of on a matrix level, we got the same exact linear system whose augmented matrix is the one shown. Now I want to keep putting this matrix in row echelon form. So I have a leading one in my first row, all 0 entries below it. Now I need a leading one in my second row, and that's going to come from this second entry. And I'm going to get it by taking 1/2 of row 2 and replacing row 2 with that. So I'm going to multiply all the entries in row 2 by 1/2. That means that rows 1 and row 3 remain the same, and row 2 becomes 0, 1, 1.5, 0, 2.5. I want to keep on my journey of putting this matrix in row echelon form. So I have a leading one in row 1, all zeros below it. I have a leading row 1 in row 2, and I want to make all zeros below it. So I'm going to take row 3 now and make a 0 in that second entry. And I do that by replacing row 3 with row 3 minus 4 row 2. That means that row 1 and row 2 stay the same, and I replace row 3. And I get, actually I end up getting all zeros when I take row 3 minus 4 row 2. So that's equivalent to the equation 0 equals 0. That meant that row 3 was just a multiple of row 2, and many of you might have seen that from our very first step. Okay, so now would come to the point where we would use back substitution, where we might Okay, so I've got this matrix in row echelon form. What I want to do is actually solve for x and y in terms of z and w. So I don't want any y's in the equation with the x. So what I really want to do is get rid of that 1y in the equation with an x in it. So in the row where there's a leading one where the x variable goes, I don't want the y variable because the y variable is also a place where I have a leading one. In other words, I want there to be a 0 there. I want this to be a row equivalent matrix where this leading one here is the only non-zero entry in its column, and I want that one to be 0. I want this to be in reduced row echelon form. Cleaning this matrix up a little bit and making it look like it used to, I'm trying to make this be a 0 entry. I'm trying to put this in reduced row echelon form, which would mean each of my leading ones is the only non-zero entry in its column. So I need to get rid of that one. And then it will be in reduced row echelon form because these are the only two leading ones. So how do I do that? I'm going to take row 1 minus row 2 and replace that with row 1. So rows 2 and rows 3 stay the same, and row 1 becomes 1, 0, negative 0.5, 1, negative 2.5. And now I've got reduced row echelon form, and this is going to help me with my final answer. I'm going to rewrite that final row equivalent matrix, spread it out a little bit, and then remind myself what this means. Take away those brackets and add in the variables. This is the equivalent or the associated linear system of equations, which cleans up as x minus 0.5z plus w equals negative 2.5, and y plus 1.5z equals 2.5. Here we should notice that z and w can be whatever they like, and then x and y are determined. X and y depend on what z and w are. So solving for x and solving for y, here are the equations we get. Our final solution would be that z is a parameter t, w is a parameter s. Oh. And after I know that, then I know that x is 0.5 t minus s minus 2.5, y equals negative 1.5 t plus 2.5. And that's our solution. Now it might seem silly. Oh, I think I wrote something a little bit incorrectly. I should say 1.5 t plus 2.5 there. It might seem a little silly that we're replacing z with t and w with s. Z is a variable, w is a variable, and t is a parameter, and s is a parameter. And those might seem similar. What we're going to get to in the future is being able to describe our solution set a little bit differently, and this parameterization is going to help us a lot. So for right now, let's just work with it and let it help us in the future.